Hello everyone, we are back with yet another interesting webinar. Before getting into the session, I would like to brief on the campus and department profile. Francis Xavier Engineering College, fondly referred as FX Engineering College, was established in the year 2000 and is located down south of Tamil Nadu in Tirunelveli district. It's an educational wing of SCAD Group, a socially committed group which works for the upliftment of underprivileged and marginalized community and founded with a vision of reaching the unreached. In Francis Xavier Engineering College, we offer 6 UG programs, 10 PG programs and have research centers offering doctoral programs as well. The campus is spacious, green and vibrant, making it ideal for learning and character building. Our institution has received grants from various funding agencies to carry out state-of-the-art research and for conducting training programs and workshops for mentoring students and faculty members of our institution and the neighboring institutions. Our college has been offered autonomous status in 2019 for a period of 10 years. 4 of our UG programs are accredited by NBA. Francis Xavier Engineering College believes in the holistic development of the students and faculty members. The Department of Mechanical Engineering was started in the year 2005 and offers BA in Mechanical Engineering and MA in Industrial Safety Engineering. The Department of Mechanical Engineering is the largest on campus with around 600 students, 35 faculty members and good infrastructure in terms of laboratories and other amenities. This department is NBA accredited and permanently affiliated by Anna University. Our department has got experienced and passionate faculty members with a rich and diversified domain expertise. In addition to the courses enlisted in the curriculum, the students are offered with various skill trainings and value-added courses to make them industry-ready technocrats and entrepreneurs. Apart from the mandated laboratories, we have well-equipped applied laboratories encouraging innovation. We also have a strong academy for training students to appear for GATE exam to get into premier institutions like IITs and NITs for higher studies and also to get jobs in public sector units. The jewel in the crown is we are ahead in breaking gender stereotypes. We have many girl students and women faculty members doing remarkably well in this so-called male-specific stream of engineering, that is mechanical engineering. Thank you. Hello again, this is Dr. Z, Professor in the Department of Mechanical Engineering, Francis Xavier Engineering College, Tirunelveli. Let me brief on the profile of today's speaker, Dr. Khalid Rafi. Dr. Rafi is a Senior Additive Manufacturing Program Development Lead for ASTM Additive Manufacturing Center of Excellence. He develops programs on additive manufacturing education and workforce development, standardization and certification. Dr. Rafi received his bachelor degree BTech in Production Engineering from TKM College of Engineering, Kerala in 1997 and postgraduate diploma in management in 2002 from IGNOU, New Delhi. He has completed his MTech in Metallurgical and Materials Engineering from IIT Madras in 2005 and PhD from IIT Madras in 2011. He has done his postdoctoral research in the field of additive manufacturing in the Rapid Prototyping Center in the University of Louisville, Kentucky in the United States from 2011 to 13. He started his career as a teaching faculty in the Department of Mechanical Engineering in PET Engineering College, Valiur from 2000 to 2006. After that, he worked as an assistant professor in the Department of Mechanical Engineering in Travancore Engineering College, Kerala. After his postdoctoral fellowship, he was offered a research position in the School of Mechanical and Aerospace Engineering in the Additive Manufacturing Center, which is now known as the Singapore Center for 3D Printing in Nanyang Technological University, Singapore from 2013 to 15. Dr. Rafi was the Global Technical Lead for Additive Manufacturing Programs at Underwriters Laboratory, Singapore from 2015 to 19. He was a key contributor to additive manufacturing training programs, development of UL Blue Card program for plastics in additive manufacturing, and in establishing qualification program for metal additive manufacturing. Dr. Rafi then became the Senior Lead Additive Manufacturing Programs Development ASTM International, Singapore in October 2019 and has been there ever since. Rafi has co-authored over 25 publications in peer-reviewed international journals and has made over 30 presentations in international conferences, symposiums, and trade shows. Dr. Rafi, an eminent researcher with huge international experience, recognition, and achievement, is among us today, and I believe that you all make use of this session effectively. Let me also take this opportunity to invite you all for this session, and I request you to keep posting your queries in the chat windows. All your questions will be answered at the end. Thank you. Now I'll turn the floor over to Dr. Rafi.
Okay, thank you. Hello, good morning, everyone. My name is Khalid Rafi, and I'm from ASTM International. It's always a pleasure to interact with the students and to share some of the thoughts on different topics. So today's presentation is basically on a technology called additive manufacturing. And I'll be covering some fundamentals and applications of the technology for the next 1 hour. And so the learning objectives for this particular webinar is to give you a fundamental understanding about these additive manufacturing technology, and then give different types of technologies comes under additive manufacturing, some of the industrial applications, then what are all the future prospects and challenges for this technology. So before moving into additive manufacturing, let us talk about what's happening in conventional methods. So we use different methods to produce parts like drilling, machining, casting, cutting, forming. So this is the way at which we currently produce the parts. So we can categorize these technologies into two. One can be called as a formative manufacturing, which involves forging, casting, stamping, and molding. And the next one, we can call it as subtractive manufacturing, where we do milling, drilling, and turning to remove material from a bar stock and get the final part. So these are the two major categorization of current manufacturing methodologies. And this is how we make parts in a mass way. However, there are some limitations of the technology as well as advantages. So if you get into the advantages of this technology, it's mainly used for mass production, and it is repeatable. We have a variety of materials available for doing conventional processes like injection molding. You can see more than 80,000 polymers available for injection molding. And since the technology is there for quite long, we have availability of larger skill force, and the learning curve in this technology is almost matured. So we need not require any additional specialties in addition to just adding some capabilities. So we still rely on these conventional manufacturing technologies, and this conventional manufacturing technologies covers around 3 trillion of the manufacturing market. However, there are some limitations for these conventional technologies. One of the main limitations that we can see is the design constraints, which means you are not allowed to design whatever you want to because of the kinds of tools that we used, because of the molds that we used. And if you want to make a small quantity of components, again, it is not economical. Also, we need a high capital investment if you want to set up a big factory with all these machines. And another aspect is on producing complex parts. For example, if you want to create a honeycomb structure with conventional processes, it's quite difficult. And most importantly, the tooling cost, the cost required in getting different kinds of molds as well as different kinds of cutting tools. So these are some of the limitations still we face in conventional manufacturing, and we need to look for solutions for that as well. So when it comes to quick design iterations, I said design is one of the main issues with conventional manufacturing. So if you want to do design changes quite often, it's quite difficult in conventional processes. Similarly, if you want to make complex designs, again, that's another caveat there. And if you look for low volume production, again, it's not that economical. So what's going to be the alternative in that case? So the solution that we can think of is about a technology which is there in the market for around roughly around 30 years. It's called 3D printing. That's the common name, people know about it. And this is a technology which currently disrupting the way in which people design a product or prototype or build products. So this technology was there from 1980s onwards, and let's see how this works. So fundamentally, this is 3D printing is nothing but creating a product by adding materials layer by layer from a computer model. This is a fundamental concept. So whatever be the technology that I'm going to discuss in the next few slides, they all work on the same concept of layer by layer addition of material from a 3D model used in a computer. So keeping that in mind, what we can make with 3D printing? Is it something trivial, or is it something science fiction based? No, we can create parts right from toys up to rocket engines. So you can find variety of applications across multiple industries using 3D printing. And some of you may be familiar with many of these technologies. So those who know about these technologies, I think this presentation is going to be reiterating your knowledge on that. And those who are new to the technology, I think this is going to be exciting for you. So you can make different things using 3D printing. So how big and how small you can go with this process? So you can even manufacture things with dimensions less than 2 millimeter, and you can even go up to 1,500 millimeter in a build. So recently you can see multiple images in here where people build boats using this 3D printing process. People use parts for aerospace applications using this process. So the application is wide range, and you can imagine different applications where this 3D printing process can fit in. So what was this process when it was originated? Even though 3D printing is considered as relatively new, but that's not correct. 3D printing is a pretty old technology, happened or invented back in 1980s. So this technology was first developed by a scientist named Dr. Hideo Kodama. He was from Japan, and even though he started working on 3D printing, but he couldn't file the patent. But a person named Charles Hull, he's the one who technically secured the first patent in 3D printing. That's back in 1984. And the technology, what they call at that time, it's called stereolithography. And even now, the technology is called stereolithography. And this particular technology is developed by the company called 3D Systems. Now, Chuck Hull, he is the founder of the company called 3D Systems, and they are one of the major players introducing equipments for 3D printing. So over the years, a lot of developments has happened, and a lot of new technologies came in. And in the past 30 years, you can see the technology has been matured from prototyping to industrial applications. So what was this technology called in the very beginning? So most of you might have heard about the term rapid prototyping as part of our mechanical engineering classes. So this technology was called in multiple names, called rapid prototyping, desktop manufacturing, direct digital manufacturing, solid freeform fabrication, and there are multiple other names if you Google it or if you look into the previous aspects of 3D printing. But the two key terms that people currently using are, one is 3D printing and another one is called additive manufacturing. So 3D printing is considered as a layman name because most of these magazines, they use the term 3D printing. But as we move on, being a technologist or being a manufacturing engineer, we use the term additive manufacturing. So why we call it as an additive manufacturing? Additive manufacturing is the official industry standard term coined by ISO ASTM committee. And there's a standard called ISO ASTM 52900, which talks about the terminology that you need to use when you talk about additive manufacturing. And this particular terminology is developed based on the nature of the process, because we successfully add materials layer by layer to make the product. That's why we call this as additive manufacturing. And as per the definition, it goes like this. It's a process of joining materials to make objects from 3D model data, usually layer upon layer, as opposed to subtractive manufacturing methodologies. So this is the definition for additive manufacturing. And moving on, in all these presentations, I'll be using the term additive manufacturing interchangeably with 3D printing. So both these terms can be used, but in a research perspective or in a industry perspective, the terminology that we should use is additive manufacturing. Now let's see what are the different categories of technology which comes under additive manufacturing. So additive manufacturing is an umbrella term, and we cannot have a single technology to solve different problems. So even in additive manufacturing, we have different categories of additive manufacturing technologies which can be used for multiple applications. So it depends upon what kind of applications that you are looking at, what kind of materials that you are looking at, and what kind of scale that you're looking at. So based on that, the additive manufacturing technologies has been classified into 7 different categories. And again, these categories came up from the ISO ASTM standard, which talks about the additive manufacturing terminology. So why people go with this particular terminologies? Because there are a lot of machines out in the market, or companies out in the market, they use their own commercial terms which cannot be used across the industry. So that's the reason why, based on the nature of the process, the AM technology has been classified into 7 categories. So one is called binder jetting. Another technology is called material extrusion. Another process is called material jetting, sheet lamination, vat polymerization, powder bed fusion, directed energy deposition. So we will be going in detail to all these processes in the coming slides. But one thing which you should keep in mind is that in all these technologies, again, the fundamental concepts remain the same. That is layer by layer addition of the material. The only difference that you're going to see is that the way in which those materials are added, or the energy source that they use to add those materials, that's a key difference when you compare each or all these technologies. But fundamentally, all the technologies follows the same principle of additive manufacturing, of adding materials layer by layer. So this is the concept I think you should understand when you deal with a small machine or a bigger machine. So all the equipments, all these machines are following the fundamental concept of material addition. So this is the first technology I want to talk to you, that is vat polymerization. So vat polymerization is nothing but we are using a resin as a material to create the product. So what happens is that based on the computer model or based on the 3D model that we gave to the system, a laser beam comes and tracks a single layer and solidifies that layer alone. So you can see the laser is now coming, and then one layer is solidified. So there is another slider or a recorder which just coat another material on top of it, and then again the process continues. So this continues until you get your final part. And another interesting thing that you can see is the solidified material that you are seeing in this violet color is different from the remaining material, which means the remaining material are untouched or it can be reused. So you can see the printed part here, which forms only the actual model that we gave to the system. So you can still have the vat. Vat is nothing but it's a vessel. That's the reason why it got the name vat. And these materials can be again reused for your next application. So that makes this process much economical. And the kind of materials used for this vat polymerization are urethanes, acrylics, and different composites. And the strength of this technology is basically you can get an accurate surface finish, accurate dimensions, and you have a range of materials. But the negative part of this process is immediately after printing this part, we need to take it out and put it in an oven for curing it. So we call this part as a green part once it just comes out of the machine, and we need to cure it to make sure that it got the right strength. And the major industrial applications here are for medical, dental, automobile, and other consumer applications. One of the typical example for a dental application is the dental aligners, the clear dental aligners that people are using to straighten their tooth. So that particular thing is now produced using the vat polymerization technology. And there are other new technologies delivered or derived from this particular technology, and they have different commercial names called DLP, that is digital light processing, or CLIP, that is continuous liquid interface production. So these are all different terminologies or different names brought out by different companies who use this particular process. But this particular process is called vat polymerization, and the common name it is known in the industry is called stereolithography or SLA, and this is the first additive manufacturing process. Moving to the next one, the next category is called material extrusion. And this is the most common technology that you can see. If you go to any college or school, if they have a 3D printer, then the 3D printer that you can see is a material extrusion based one. So here, what happens is that one filament is extruded through a nozzle and deposited on the platform. So again, it deposits one layer first, and the table moves a little bit down based on the layer thickness that we give, and it keeps on building the layers until it makes your final part. So here you can see two colors. One is a dark blue and another one is a light blue, which means you have two different materials used here. One is to print the actual part, and the next material is to support if any overhangs or any light features. And once you print this part out, you can take this part and remove the support material. So there are different ways to remove the support materials. You can simply put it in a solution so that it will dissolve in the solution so that you can get your final part. So these particular technologies now used for a variety of applications, starting from prototyping to end-use productions as well. So one of the strength of this process is that it got production-grade materials. We can have a range of materials available, and we also have dissolvable surface. Means in additive manufacturing, removing or taking out supports are one of the biggest tasks. And the weakness of this process is that we cannot use it for any high strength applications. And the speed at which this process works is relatively slow because each layer is only a few microns. And if you want to add few, let's say few centimeters, then it will take some time to get the part printed out. But now that particular aspect is solved by using multiple printers in tandem. They call it as print farms, where you have 50 or even 100 printers laid in parallel and do the work. So main industrial applications are basically on tooling and consumables. And the common name for this technology is called FDM. So that's a name that most of you might have heard about. It's called fused deposition modeling, or another name is FFF. That's called the fused filament fabrication. So this is one of the most common technologies that most of you might have encountered before. Another technology is called material jetting. So I would say this particular technology resembles pretty similar to what we do with our 2D printers. So in 2D printer, we use an inkjet cartridge and we print a picture. Just imagine that after printing a picture, you keep on printing on top of this picture so that you will get a 3-dimensional image of the picture. So the difference here is that imagine that you remove the print cartridge and add in a cartridge which contains plastics, or which contains resins with different colors. So this is typically called as a 3D printing process in the very beginning, because it actually 3D prints right in the build chamber itself. And another advantage here is that you can see a light coming just after this. So that is a UV light. So that UV light cures each layer immediately after printing it. So this is a big difference between this material jetting process and vat polymerization, where in vat polymerization, you have to take out the green part and put it in an oven to do the curing process. But here, you will get it cured within the machine itself. So one of the strengths of this particular process is that very good surface finish and accuracy. And most importantly, we can have colored cartridges so that we can get any product with any desired colors you want. So the main industrial applications for this technology is mainly prototyping, product development, and for marketing purposes. So when you do a product development, and if you want to make sure that your customer would like the product, then you can have all those varieties of colors in this product. And another advantage is if you want to make small changes, you can always make by tweaking the design a little bit. So that is one of the advantages, not just for material jetting, but all 3D printing processes. The next technology is called binder jetting. So in the previous one, what we saw is material jetting, which means you jet materials and you add materials layer by layer. But here we are not adding material, but rather we jet binders. Binders mean they are glues which can stick to 2 layers of material so that it can get bonded. And this is a technology where we can use multiple materials. We can even use sand, we can use clay to produce a part. So the animation that you are seeing here is basically a process of creating a sand mold. So what you're seeing in this light yellow color is a layer of material. So once one layer of material is spreaded, now we have a print head coming up, and the print head will dispense the glue so that only that layer of sand or only that layer of material will get glued. And in the next step, you will be seeing another layer of powder material coming on top of that, so that those regions will get glued together. And this process again continues until you get your final part. So you can see the next step where there's another powder layer coming up, and this is called a recoating. And again, you can see the head coming and dispensing the glue. So this continues, and you'll get the final product. Finally, I can make it a little faster. So this is mainly used for creating sand molds. So as mechanical engineers, we know the pain in creating sand molds, but now we can do 3D printing of these sand molds. And more importantly, we can create a lot of complicated structures in this sand mold. So this is one of the technology which is now used in large industrial companies to create bulk structures on castings for casting. So here you can see a typical image of a sand mold which is created using binder jet. But the weakness of this process is that it is a multi-stage process, which means once you finished creating this product, it's only glued with the binders. It's called a green product, or it is very fragile. So what we have to do is, after this, we have to take it to a chamber where you can do a sintering, not sintering, but you unbind the glue first. That's one stage. And there's a second stage where you have to sinter this part so that you will get the right strength for the application purpose. So it's more like a 3-stage process, but it's more useful when we go for creating sand molds with complicated structures. The next technology is called powder bed systems, and this is one of the most widely used technology for industrial applications. So how it works is pretty much similar to the thing that we saw earlier, where a layer of powder is spread, and there we use glue. But in this technology, we are not using glue, but we use lasers to laser or electron beam to bond 2 layers together. So for example, if you see this animation, one roller came and brought some material on top of this table, and then a laser beam comes down and melt only 1 layer based on the design that we give. Again, another layer of material comes in and create the next layer. So this keeps on going until we get the final part. So, and the advantage here is that, same as what we have seen in the vat polymerization, only the required material is used for producing the part. We can reuse the rest of the material by taking it to a depowdering station, where you can just take out all the powders by using a sand blaster, so that you will get the remaining part. And for our next build. So this particular process is mainly used with polymer as well as powder. So there are different terminologies that you might have heard about this process. One is called selective laser sintering, where we use polymer powder. And there is something like selective laser melting, where we use metal powders. And electron beam melting, again, we use a metal powder, but the difference is the energy source is an electron beam. So here, each layer is somewhere around 40 to 50 microns thickness. And you can compare it as a micro welding, where this laser beam comes, melts, and solidifies a layer of material based on the design that we gave to the machine. So the strength of these particular process is that you don't require any support material if there is a curvature, because we already have some powder. But this applies only for polymers. But when it comes to metal, still we need some supports because of the high density of the metal. And we can print multiple designs in a given build chamber. And for part strength, for all functional applications, whenever someone asks for doing something for 3D printing for a functional application, this is going to be the first preferred technology. And the weakness here is that you have to control a lot of parameters. For example, in a laser process, it contains somewhere around 100+ different parameters, which could affect your final part. And the important industrial applications here ranges from prototype to functional and structural end-use parts. Another technology that we can call under additive manufacturing is directed energy deposition. This is pretty much similar to your plasma deposition process, where we use a plasma to melt a weld rod. The same concept applies here. So you can see a laser beam, and into the track of the laser beam, we provide fine powders. So it will just deposit, again, layer by layer, only the place where we need to deposit the material. This process is mainly applicable for repair and reclamation of the parts. So we need not to throw away any industrial component which got degraded over the years. So we can use this technology just to build additional or to replenish any additional material to that. And this technology, I would say, it's the first technology under metal additive manufacturing. But now this technology is gaining interest in multiple industries because of its capability to build large structures. So here, as I said, the material used are metal powders, and the strengths are we can have multiple metals. We don't need any supports, and we'll get fully dense parts. So this is another technology which has been used for aerospace applications and marine applications quite a lot nowadays. And the last technology, it's called sheet lamination. So this technology is not that popular, but mainly used for prototyping, where you can make a product by stacking some sheets. So the sheets can be anything. It can be paper, it can be metal foil. Depending upon the kind of applications, you can choose the material. So what happens is that you'll be having a paper, for example. At first, you will keep on stacking a paper, and either a laser, so in this image, you are seeing a laser, or a sharp blade will come and trace the paths according to our design. And each paper is glued together so that at the end, you will get a final part. So you can see an image right below, which shows the model of a car. So this is basically made by this sheet lamination process. So one of the common name for this process is called LOM, that is a layered object manufacturing, if you're using papers or polymer films to do it. But if you use metal foil, then you call it as ultrasonic consolidation. There we are not using a laser, but we use a thing called a horn, which can bond two metal sheets using ultrasonic energy. So these are the multiple technologies that you can see under additive manufacturing. So where additive manufacturing stands now? So we have seen different technologies under additive manufacturing. We have seen the capabilities of additive manufacturing. One of the major capabilities are to add material in fine layers. The layer thickness is somewhat closer to the thickness of our hair. So the advantage of having those fine layer thicknesses is that we can go for very fine features, let's say about 500 microns or even 300 microns. So that makes this technology more acceptable and diverse when compared to the conventional processes. So when it comes to applications, where we are, is it still a prototyping tool, or are we moving ahead with industrial applications with this technology? So if you see additive manufacturing, it is now everywhere. You name in toys, or you name in aerospace. In all these industries, you can find some applications using additive manufacturing. So these are some of the typical industries who use additive manufacturing. So typically automotive, defense, production, aeronautical, medical, consumer. We will see each and every industry in the coming slides. So starting with aerospace, so this is the one industry which embraced this technology in the very beginning because of obvious reasons in creating more value to the industry by saving a lot of cost. So if you know that if the air bus companies or the aeroplanes, if they can reduce at least 1 kilogram of weight, 1 year they can save more than $1,000 by saving 1 kilogram of material. So there are a lot of areas where additive manufacturing can be used for aerospace applications. So initially they were used only for non-critical parts or cabin parts. So even now, most of these aircraft companies, they are now using additive manufacturing for producing a lot of cabin interiors. And now additive manufacturing is also used for making engine components like turbine blades and things like that. So as I said before, if you remove 1 pound of material from an aeroplane, they are saving 14,000 gallons of fuel each year. Imagine the case of a big company who is having a large fleet of aeroplanes. So that's the reason why aerospace companies started using additive manufacturing as one of the major technologies. And now I would say this is more or less matured in the aerospace industry, and more than 5,000 small components are now started producing using additive manufacturing in Airbus as well as in Boeing aeroplanes. and other companies, other aeroplane service companies like Etihad Airways, or even Australian Airways companies in Australia, New Zealand, they're all trying to use additive manufacturing for their they call it as repair and overhaul for the aircraft, which can save a lot of money and time for them. And another advantage is they need not to keep a lot of inventory, so they can produce things just in time as required. Another important application area is on medical. So you can see different 3D printed implants which has gone into patients' bodies. So it's almost 10 years now that people started using 3D printed implants. For example, there are some knee replacement and hip replacement implants, and these are the two major surgeries that you come across when it comes to orthopedic surgeries. So now 3D printing is used for creating or even producing those parts. The advantage is that we can have these implants based on our anatomical features. We need not to get off the shelf products which doesn't fit to our anatomy. So somebody can scan your knees and then create a knee implant based on your dimensions. Similarly, we are using it for creating prosthetics, matching prosthetics. So previously, if you have a hand breakage, then you will be having a big casting around your hand. But now you can have some fancy prosthetics which applies to your hand. Similarly, for dental applications, and can be used by doctors for for printing medical guides. And one of the important applications some of you might have observed recently is during this COVID-19 situations, where 3D printing has been used very widely for printing face shields and face masks. So we need not to wait for a company to produce and ship it to your place. So they started using 3D printing to produce those face shields and face masks. Similarly, in automotive, there are different companies now started using additive manufacturing for producing different components for automotive. It's not just for our regular automobiles, even for people working in fast track processes. They are using additive manufacturing to make some components. And recently, companies like Audi, they started customizing their cars based on what you want. So they can customize the dashboard for you. They can customize your steering wheels. So they are now allowing you to choose 16 different components in the cabin of the car so that they can customize it for you. And another one is wearables. So some of you might have seen this thing before. So this is a 3D printed shoe. When I say 3D printed shoe, only the sole of the shoe is 3D printed. And the advantage of the sole is that you can have variable structures varying from the toe to the tip, so that you can have different comfort levels. So this is one of the important applications when it comes to shoe manufacturing. So previously we were relying, or most of the countries were relying on China to print these kind of shoes. But now these shoes are printed in America as well as in Germany using multiple machines. So you can see Adidas recently came out with 3D printed shoes, and so many other companies are also now started using 3D printing to print the soles for these shoes. And another important thing is on tooling. So we can use, or we can produce tools just in time or as required. Most of the time, if you go to a company, their warehouse will be full of different tools which they may be using once in a year, or they may not even use for years. So that will take up, more than 25% of their total inventory. So one of the important thing that people are now trying out with additive manufacturing is to reduce the inventory, so that they just print or they just manufacture the tools as and when it is required. So tooling is another major area where 3D printing is, or additive manufacturing is finding a lot of applications. Next is fashion. So the fashion industry is also getting overwhelming response in using 3D printing. So recently, some of these fashion shows, they started demonstrating how 3D printing can be used to come up with versatile designs in fashion as well. And the last one is construction. So 3D printing in construction is another major area where industry are gaining importance. So 3D printing can be mainly used for mass customization. That's a general term that we use to producing parts using 3D printing, but this is used for mass housing in construction. So let's say you want to build some hundreds of houses in a rehabilitation place, then 3D printing is the viable option now to create smaller houses. The one image that you can see in the left is a 3D printed building. They called it the first 3D printed building in Dubai, and there are countries which have vision to build 25% of their total buildings using 3D printing by 2030. So 3D printing in construction is another important area where people can look on. So we have talked about different technologies, different applications, different potentials, but still additive manufacturing is not fully into the manufacturing stream. There are many reasons for that, and we can categorize that into technical and commercial. One of the important technical reasons that you can look at it is the lack of talent and current expertise. This is where people who are right now studying mechanical engineering can look on. So there is a deep dearth of talent in additive manufacturing, so people can look as an opportunity in the future. Then there's a lack of awareness and understanding on when to use AM and which technology to use. So people feel that additive manufacturing can replace conventional manufacturing, but that is totally wrong. Additive manufacturing can only substitute or only complement some of the areas in conventional manufacturing. And you cannot use additive manufacturing for everything. So we need some kind of specific purpose or some kind of specific need to use additive manufacturing. So before somebody get into additive manufacturing, they should have an understanding about what or when to use additive manufacturing or which technology you should go for. Another aspect is on the printing speed. So as I said, the process is relatively slow because you are adding material in a layer by layer fashion, and each layer is somewhere around 50-60 microns. So you can imagine that how much time it will take in order to make a big product. But now printers or new equipments are coming which can fasten these printer speed, or which are having large build volumes where they can accommodate more components in a single build. And another aspect is people are a bit uncertain about the quality of the product, because we don't have any past data to validate the quality of the product that we made using additive manufacturing. So we need qualification and certification in this space, but things are a little unclear on that. And there are lack of regulations and standards on additive manufacturing, and this is where ASTM International is working on. So we have a committee called ASTM F42, which specifically focus on additive manufacturing. And so far, if you search, we have more than 25 standards published, which can help industry to move forward. And the commercial implication in AM adoption is mainly the cost. If you go for a production machine, let's say if you want to have a metal additive manufacturing machine, it costs somewhere around $1 million US. So that costs a bit, but as the time goes, as the technology advances, the cost is coming down a little bit. And second aspect is identifying a business case. As I said before, people should know where they want to use additive manufacturing. So then only they can create a business case to use additive manufacturing, and the supply chain is not in place. There are IP issues, and there are issues like export control and insurance, because insurance companies are a bit reluctant to underwrite the risks for this particular technology, because again, they don't have enough data to support the claims. So even now, insurance companies are a bit reluctant, but they are now getting up to speed. Then most importantly, there should be a need of change in the mindset for adoption. So we are comfortable with our conventional manufacturing processes, but when we get into a new technology, people are a bit reluctant to change. They still are skeptical about the outcomes of this technology. So we need to have a change in mindset to make sure that this technology can be adopted and put it along with the existing manufacturing ecosystem. And what we can see in tomorrow, So some of the industrial applications that we envision are on biofabrication, which means you can use 3D printing for fabricating body tissues or human tissues. So this is an important research area where people are looking to 3D print human body organs. So they already started printing skins. They started printing parts of muscles. So right now, those products are used for pharmaceutical applications where you can apply a medicine in that skin rather than applying it directly to the body of a person. So biofabrication is a major application area, or we call it as a bioprinting, bio 3D printing. And electronics, that's another area where you can have wearable electronics. For example, right now, if you see the shape of a battery comes either as in a cylindrical shape or in a square shape. Let's say if you want to have a wearable watch, and if you need a flexible battery, right now that's not there. But 3D printing can now produce batteries which can have any shapes. And another thing is mass customization, which means we can cater the requirements or the needs of each and every individuals based on their taste. They need not to really look on a set of standards. For example, if you go and buy a shoes, you cannot have the sizes that you like. For example, the size after 7, the next size is 8. So if somebody needs to have a perfect fit by 7.5, there is nothing like that. So you can have mass customization on multiple products. And another aspect, as I said before, is construction, where you can build custom-based buildings in a faster pace. And more importantly, additive manufacturing is going to be an integral component of Industry 4.0. That's the next industrial revolution. And coming to the process side, we are going to get faster and more sophisticated machines. And we can have in situ process control, which means while the process is going on, we can keep changing on the process to make sure that your end product will be error-free or will have all the right properties. And there are also advancements in coming out with latest materials, because if you see right now in 3D printing, the materials that can be used are very limited. So now another important research area is on coming up with advanced materials for this process. Okay, so this is all from me about this technology. I know that it's quite difficult to get an overall understanding about the technology, but what I try to do here is to give you a snapshot on what is there in additive manufacturing and what is the technology is all about. So with this background, I think you can do research to learn more on this topic, and you are welcome to reach out to me. Here is my email ID, that is krafi@astm.org. So at any time, if you have any queries with regard to the technology, please feel free to reach out. So having thank you very much for your patient hearing, and thank you very much FX Engineering College and the Mechanical Engineering Department to provide this opportunity to share my thoughts with the student community. Thanks again.
Thank you, Dr. Rafi, for the wonderful presentation. We have some questions from the participants. Okay. Can we go ahead?
Absolutely.
Yeah. The first question is from Dr. Saxena. Is additive manufacturing cost competitive compared to conventional processes?
So again, as I mentioned a bit early, so we are not considering additive manufacturing as a competitive one. We are considering additive manufacturing as a complementary one. So even after additive manufacturing, you have to do some kind of post-processing where we need to use conventional manufacturing like milling or all kind of polishing and things like that.
Okay. The second question is from Mr. Sajid Nair. Uh, what about the surface finish that can be achieved on AM components?
Good question, and I think it will add up on my previous answer. So additive manufacturing components, if you see it right out from the machine, you can see the surface roughness are not that good. And most of the time, we are not using additive manufactured components right after the machine built. So we have to do some post-processing. And the main reason for the surface roughness is because of this layer by layer addition of the material. So that layer by layer addition causes a process called stepping, and we need to remove it by using a conventional process like milling or some kind of surface polishing. But nowadays, we are trying to get materials with very fine characteristics or with fine particle size, which can improve the surface roughness so that we can come down to 10 microns. So the best surface roughness that you can get out of additive manufacturing is somewhere around 16 microns, and that applies to the technology called material jetting. But otherwise, the surface roughness is a real issue with additive manufacturing, and obviously you need some kind of post-processing.
Thank you. And here's another question. You mentioned it clearly that we are adding layer by layer of materials, right?
Yep.
Is it possible to detect a missed layer?
So it's not like there is no way to get a missed layer. Only thing is we can expect a defect in the layer. So,
exactly.
So what happens is that when we tell the machine to print a part, we are not giving the machine a 3-dimensional information. We are giving the machine a 2-dimensional information, which means every time the machine is getting an information to print a single layer. Okay, so if there is something missing in the actual design, definitely you will be having a layer missing in this part, and that will obviously becomes a defect or a porosity or things like that. But otherwise, from a machine perspective, we are giving or we are instructing the machine to print a single layer. So machine doesn't really know that it is printing a 3D object. It only knows that it prints a 2D layer. So in that way, the possibility for missing a layer is not there. But again, if there is a fault in a layer, now we have capabilities in most of the machines to track each and every layer and what's happening in that layer. That's called in situ monitoring. So many machines are now coming up with those capabilities.
Thank you. You have mentioned it clearly that we are doing some post-processing operations, but Prashant is still having a question. I just want to reiterate it.
Okay.
Can secondary operations possible on AM parts?
Yes, so there should be some secondary operations. For example, we need polishing, we need some other finishing operations. But another thing is that let's say we have to build a big component, and most of the time the build envelope size limits us from doing that. So in that instance, we have to make these two components separately, and we have to join it. But it's highly unlikely of such situations. But most of the time, we select components which can be built within a given build volume, so that we can integrate multiple components. So one of the key advantage of additive manufacturing is product integration, where you can have, let's say, integrate 15 or 20 components to make it a single component. But again, as you said, secondary processes are necessary. We cannot simply live without those secondary processes, even we go with this additive manufacturing process.
Thank you. You have mentioned clearly about the limitations, like the products that cannot be or should not be manufactured by AM.
Yeah.
Just curious to know if there is there are any specific issues in after processing. Like when I get through some papers on this topic, I came to know that there is an issue like on the heat treatment of AM components. Like they have observed some cracks, especially in nickel-based alloy AM components.
Yeah.
Can you please brief on that?
Okay, so when it comes to heat treatment, again, most of the time, the kind of microstructure that we are getting out of these 3D printed components are entirely different from what we get it from conventional parts. So the kind of microstructure that we are getting there is a columnar microstructure. And if you want to get the right properties, definitely we need to go and do some heat treatment. So there is no specific heat treatment methodologies right now available for additive manufacturing. We still use the AMS specifications that you use for conventional heat treatment processes. So people are now trying to figure out what would be the right what do you say heat treatment process. So particularly when it comes to alloys like Inconel and things like that, there are possibilities for getting cracking because of this specific microstructure that we are getting out of this 3D printing process. So we need to have specific heat treatment methodologies for additive manufacturing as well. But right now we follow the AMS specifications, and it's good with that. But the cracks are mainly, one reason could be a porosity which is already there during the process, and one reason could be the inclusions. So most of the time we may not get 100% dense parts. So those all things could lead to a crack formation in a finely printed part.
Thank you. And there is a question from Tom, maybe a continuation of the previous question.
Okay.
Could you please brief on the NDA, non-destructive evaluation, for certifying AM products?
Okay. So NDE is another important topic that we need to address in additive manufacturing. So the most commonly used NDE technique is called CT, computer tomography. And the advantage of using CT is that we can go and detect layer by layer defects. But now there are also other technologies are used for NDE. For example, we are using this radiography and things like that. But the only constraint here is that you cannot get, or you cannot just use one technology to get all these NDE results. So we have to use a combination of NDE technologies to detect a defect within an additive manufacturing component. But having said that, the most common method used for detecting any cracks or defects in additive manufacturing is CT or micro CT.
Thank you. This is a question from Dashit Desai. What type of binders are used in binding jetting?
Okay. So most of the time, the binder material, so they simply call it as glue, and that is highly proprietary. That makes different companies different because they have a differentiator between another company. So most of the time, they don't reveal what kind of material that they're using as a binder. So basically, binder act as a glue, and it is going to be a polymeric resin. And these polymeric resins, once they build the part, and then when we go for debinding, that polymer resins will be debinded out of the product. So there are many companies who are having who are using a binder jet process for different applications, but most of the time they don't tell you what exactly the composition or what exactly is the name of the material that they used for binder jetting, but they have proprietary materials as binders.
Thank you. Varamani wants to know how to specify a 3D printing machine.
How to specify a 3D printing machine? Very good question. So, so far, if you see the specifications are mainly on materials, I would say. And when it comes to machine, there are no specific machines. But if you want to order a machine, let's say if you want to order a metal A machine, then first of all, as I said in the beginning, you should know what's the purpose of the machine that you're going to order. If you're going to produce some functional parts, then you should go for a machine with a multi-laser. Or if you're going for a research project, for example, in universities, you may not require a machine with multi-laser. You may go with a machine with a single laser and with a small build volume. So mainly the specifications depend upon what you want to do with the machine. So accordingly, different OEMs can give you different range of machines, and there is no standard for specifying the machine. So specification of the machine mainly depends upon what's your end use. And basically, you should be talking about the kind of the build chamber size, the laser capacity, the kind of material that you can use. So these are some of the things that you need to have as a basic understanding when you specify a machine or when you put a specification to order a machine.
Right. There is a question from Mubin Sheikh. What do you mean by when you said IP issues as commercial challenge for AM?
Okay.
Could you brief on
that? Okay. So when it comes to IP, it's more like the design. So when I create a design, and if the design is online, or if it goes to internet, then anybody can access it. So essentially, I created the design, and the IP should belong to me. But people can, or anyone can download a design at any part of the world and print the part. Or they can see a part and then scan the part and then make their own design, or they can just copy that design, because we have 3D scanners available in the market. So somebody can use a 3D scanner and scan one of the design which I used, and then it can be recreated. So at this moment, there is no clear-cut way to track that, unless otherwise you put some some kind of embedded stuffs in the design so that nobody else can recreate it. But otherwise, there are high chances for you to get your IP taken away by someone else. So that's a real threat for the designers who design particularly nice, complex shapes for multiple applications.
Okay. There is a general question on the role of AM in Industry 4.
Mm-hmm. Yeah. So as you know, Industry 4.0, we generally call it like that, is the next, or not the next, is the revolution that's happening in manufacturing, which encompasses multiple additive, not multiple additive manufacturing, but multiple advanced manufacturing things like robotics and automation. It also includes cyber physical security. And when you talk about Industry 4.0, one of the main concepts of Industry 4.0 is to come up with a smart factory. Smart factory, or people call it as a factory of future, where all these machines interact by itself. So in that chain, additive manufacturing machine is an important component, where, let's say, if you have an additive manufacturing machine in the manufacturing chain, so that additive manufacturing machine can be integrated with the existing manufacturing machines, and can also be integrated with cobotics, cobots, and other robots in the manufacturing floor. And another important thing is that all these machines can be integrated through the factory of future concept. So additive manufacturing is now becoming more automated. So previously it was more like what is silo kind of a thing. Now the additive manufacturing equipments can be made interactive with existing manufacturing systems, and can be an integral part of that factor future. So that's what I meant being additive manufacturing as a part of Industry 4.0.
Thank you. And there is a question on, can you please list on some of the simulation softwares used in AM?
Okay. So softwares are another bigger things in additive manufacturing. So we call it as a digital thread. So additive manufacturing mainly encompasses with multiple stages, and each stage is governed by multiple softwares. So there are some simulation softwares by, again, the big software companies like ANSYS, Autodesk, so and Dassault Systems. These are some of the major software companies who work on additive manufacturing. So if you see ANSYS, they have a software suite called ANSYS Fusion 360, which talks about modeling, and also they have different modules in that software where it can simulate your process as well. Similarly, in ANSYS, they have specific softwares. They call it as additive manufacturing suite, where you have different modules which talks about simulations, not even just process simulation. They can also simulate the microstructure. simulate the kind of deformations that you can see in these products. So that's about ANSYS. Similarly, in Dassault Systems, so they also have different suites, and similarly from Siemens and Next Software, they also have different software. And there are other companies other than these big boys. There are other companies who specifically work on additive manufacturing process simulations. I think if you have time, you can just Google on companies like Link 3D, 3O Mind. These are all some of these companies who focus specifically on the entire process simulation.
Okay. I think Dinesh is a research scholar, and he's asking, he needs FDM filament for research purpose. I don't know if you could be able to answer it. Where can I get it from?
I would say getting filaments is the most easiest thing for from a material perspective in additive manufacturing. So if you go to Alibaba or any kind of such material, online vendors, there are thousands of suppliers who can provide you the filaments. But the caveat here is that when you work on specific systems like machines from HP, then you have to use the filaments supplied by HP. You cannot use other machines filaments. And the type of equipment that you use, if you use a normal desktop printer, then you can try out any filament that is available in the market. And again, when you choose filaments, you should also know what is the capability of your equipment. For example, if you're just working with normal ABS or PC, then any desktop machine will help you. But I think since you're doing a research, it would not be ABS or PC. It could be something like, I believe it should be something like a higher engineering plastics, which may not work in some of these desktop machines. So you should be careful about the materials properties before you purchase it and the equipment that you're going to use. And with regard to purchasing it, it's quite easy. It's available online, and these filaments are the most easiest available materials for 3D printing.
Thank you. I have a question. If someone is really interested in making a career in additive manufacturing, it could be higher studies or a job.
Okay.
What more is needed apart from having a degree in engineering in the relevant streams? So it could be mechanical engineering, production, or manufacturing engineering. What more is needed?
Okay, so I think I used to get these questions quite often, and most of the time people feel that you should go for a specialized course on additive manufacturing or masters in additive manufacturing to get into additive manufacturing. I think that's a wrong concept. I think that's a wrong concept, I would say, because additive manufacturing is not just about additive manufacturing. Additive manufacturing is about design, it's about materials, it's about metallurgy, it's about software. So it encompasses so many things. So which means, let's say if you have a design, if you have a master's in design, I think that's good enough for you to get into an additive manufacturing design, because that's a huge, big area for additive manufacturing. Similarly, if you have a good enough background on materials or on materials engineering, then 80% or 70 to 80% of the work happening in additive manufacturing is based on materials. Similarly, if you have a software background, you can see all the process modeling happens based on your background on software. So there is nothing like a degree in additive manufacturing, because if you go for a degree in additive manufacturing, it will only give you, again, an overview about how the process works, what are the different processes available. But if you want to be into a specific area, and if you're really interested to get into that, I think any post-graduation or any further studies on design, materials, software, and even mechanical engineering in general would be sufficient. Even fluid dynamics. So there are modeling happening on different aspects of material processing in additive manufacturing. So what I would suggest is that don't be specific towards doing a master's in additive manufacturing, but whatever I just discussed, a background on these would be good enough to get into additive manufacturing.
Fantastic. Mean to say there is no shortcut or a quick fix. Is that right?
Yeah,
you need to know everything. Yeah.
Yes. So again, once you have the knowledge on everything, then you can just scale down to what you exactly want or what you are passionate about it. I think that's the way you should look at it.
Right. and someone is interested in knowing the universities across nations with good scope for like doing MS or PhD, like foreign universities and in India.
Okay. So, yeah, I'm not a good academician at this point, but again, based on my background or my understanding, is that yeah, as you know, why you want to do a master's outside, or why you want to do a master's inside, you have to answer that first. So the main reason why you should do a master's outside is to get a job outside. I think that's the reason why many of the people who are coming to Singapore or who is coming to US, they all know that getting a job is quite difficult by applying from India. So the shortcut to get into a job in any countries outside India is to get an education or get a degree from that particular country. So that's the reason why most of the people are now moving towards the US or to Singapore. But having said that, your intention is to be in the technology and to be in India. I think we have wonderful institutions in India as well. But again, if your motivation is to explore the world, is explore more into these technologies, obviously the destinations are US, Australia, Singapore, and UK. But yeah, I think most of you know what should be the basic requirements to reach there. More than your academic credentials, you should have a right GRE, TOEFL scores. I think that's quite common and everybody knows that. But again, choosing what you want to learn, that's another important thing. So based on the recent advancements in manufacturing, so we have advanced manufacturing. We are not talking about additive manufacturing alone. We have advanced manufacturing. We talk about data. We talk about data analytics, machine learning, and things like that. So there are some good courses available on these areas, particularly outside US, which I think if you're interested, then you should look upon that. And again, it all depends on where you want to go at the end of the day.
Okay, thank you. And that's all from us. Thank you so much, Dr. Rafi, for your wonderful presentation and your graceful clarifications on the queries of the participants. We appreciate your presence here. Thank you so much.
Thank you very much, and it's my pleasure.
On a closing note, I place on record my sincere appreciation to Dr. Rafi for being a part of the expert lecture series organized by the Department of Mechanical Engineering. It was indeed inspiring listening to you, and it was an excellent session. Thank you again. I would like to thank all the participants for your continuous support and excellent participation. I'm sure that you all have enjoyed the session thoroughly. On behalf of the Department of Mechanical Engineering, the faculty and students, I express my sincere gratitude to the management, the organizing team, and everyone associated with us. A special mention goes to Mr. Jason, our student volunteer, for the web screen presentation throughout the series. It has been a pleasure being interacting with you all for like a month now through this webinar series. Thank you all for your patience in responding to all our initiatives. I also want to make a point here, an important note. Please keep visiting this channel in the future. All the webinar videos are archived and can be watched anytime. We had many interesting webinars, and most of them were on trending topics delivered by the professors from IITs and NITs, and also from expert members from reputed organizations. These webinars in fact give a lot of scope for the viewers, the participants, either to identify their research area or to get their doubts clarified. Please keep sharing this link to your fellow researchers, students, and peer members. All our speakers are willing to support you with your research in the future, so please make use of that privilege as well. If you have subscribed to this channel, FXEC Mechanical, you will be notified about our future initiatives. Until then, stay home and stay safe. Thank you.